Okay, welcome back. We are moving on to section 7.4, where all of a sudden, in section 7.3, our lives were easy because we can actually perfectly calculate the solution up to, taking some antiderivatives of capital M and then another antiderivative against the inhomogeneous term. We can perfectly calculate the solution to any first order ODE evolving in one dimension. But when we get to higher order ODEs, we can't do that anymore. So we take some subsets, and the first subset that we're going to look at is called constant coefficients. Okay, so what does it mean to be constant coefficients? Well, we're looking right here. At the beginning of the chapter, we put an m sub j of t in front of y, the jth derivative of y, and that was saying that you could multiply. That's why I was using m. Multiply by any function of t on all of our derivatives. Like a nice example of this would be like cosine of t y double prime minus sine of t y prime plus e to the t y equals 7. Something like that. But, each of these is a function of time. And turns out we no longer can solve these in closed form once you get to second order. In first order, we saw that we can actually do that for functions of time. In second order, we don't know how to do this in general. If we decided to convert the second or higher order equation into a first order one involving in higher dimensions, all of a sudden this is where the Magnus expansion shows up. And we all know how nice the Magnus expansion is at trying to solve these. So we can't do this for arbitrary multipliers in higher orders, any order greater than 1. So what we do instead is we restrict ourselves to a sub j. So now we just have something like 3y double prime minus 2y prime plus 11y equals 7, or something like that. And we can, even add higher orders, 17y triple prime, and then we could do like 24y 4 primes, and so on. But as long as each of the coefficients that we're dealing with here are constants, that's what it means to have constant coefficients. And in fact, what's on the right-hand side, I shouldn't have necessarily used a 7 on the right hand side here, because this could be 7t, it could be 7t plus cosine t, etc. The right hand side, we don't care. The inhomogeneous part is fine. It's the coefficients on the dependent variable, or the function we're trying to solve for. Those are what we need to be constant to consider ourselves a constant coefficients ODE. So that's what we're going to be trying to solve today. And we've got a really nice, efficient way of doing this. So I'm gonna scroll down and define this thing called the characteristic polynomial, or the characteristic equation. So we're going to start with just our constant coefficients ODE. We've got all these a sub j's, and those are our constant coefficients. All we do is replace y with the j derivatives on it with lambda to the j power. Okay, so lambda, just like in eigenvalue equations, right? This turns out that they're kind of the same thing. That's why we're calling it the characteristic polynomial. So it's like we're looking for eigenvalues with an eigenvalue equation to the j power, and we just replace every y with one of those lambdas. The right-hand side, f of t, we're not going to worry about it right now. We can, for example, just let that be 0, because we're trying to find a fundamental set of solutions. And with a fundamental set of solutions, we only care about the associated homogeneous differential equation. So we can let this differential equation be homogeneous, in which case the characteristic polynomial, so the left-hand side is just the polynomial. If we let our equation be the associated homogeneous equation, it becomes the characteristic equation, right? An equation is when it's actually set equal to 0. That's our characteristic equation, and we're going to try to find the roots of, or the solutions to this equation, which is equivalent to the roots of the polynomial. So this is a very important thing to have when it comes to constant coefficients problems. And we recover this nice proposition, which is very, very elegant, and you'll prove it, is that this characteristic polynomial truly is the characteristic polynomial of the matrix that would result if we decided to convert our nth order problem into a first order problem in n dimensions. So that's why we call it the characteristic polynomial, because it truly is the same, and you'll prove that in one of your exercises. But the nice thing is that since this is a polynomial, it's an nth degree polynomial, we know that we have exactly n roots. Right? By the fundamental theorem of algebra, this is the whole reason why I was basically forced to give you some complex analysis at the beginning of this course, is because the fundamental theorem of algebra only works in complex analysis, and we get these b sub k roots to our characteristic polynomial. And I know you're all very used to this because we have been working on it the whole semester. Something different about the way I've phrased this, though, is that I've phrased it now, instead of just saying, okay, I have some set b sub k, and I'm going to take the product over all of the lambda minus b sub k's. Now I'm including this alpha sub k in the power, and the alpha sub k's are going to be the multiplicity of each root. So now I want to factor it using the fundamental theorem of algebra, and I want to keep the multiplicity inside of my factorization. The reason why I want to keep the multiplicity inside my factorization is for the following theorem. The following theorem says if I have a constant coefficients homogeneous ODE in one dimension, then I actually have a solution so long as I can find b sub k. Don't forget, b sub k's are the roots of my characteristic polynomial. Alpha sub k is the multiplicity of that specific root. Okay, so for each root I have, I'm going to gain an exponential, and for the multiplicity of that root, I'm going to gain a sum of powers of t in front of the exponential. So let's say maybe something, for example, if my characteristic polynomial was factored into something like lambda minus 1 squared, lambda plus 1, then my solution takes the form, well, lambda minus 1 is squared, so that has multiplicity 2. My solution takes the form c1 e to the, this would correspond to lambda equal to 1, the root t plus c2 t over 1 factorial e to the t. So that's this is my multiplicity 2 term. And then I recover the multiplicity 1 term, which corresponds to -1 for lambda. So I have e to the negative t. So that's like a nice example of how we would do this in action. And I realize with the summation notation, it can get maybe a little bit tricky to decipher. But that's how we want to think about it, is that maybe I'll make it a little more clear. The 2 here is why we have 2 terms here. So the 2 multiplicity gives me my 2 terms, and in each term I step up by t. And then the other term is left over. Okay, so let's look at a corollary then. So a nice corollary, because this is technically a theorem. It's only proving my solution for homogeneous equations. The corollary then basically states, okay, fine, I can actually solve this for inhomogeneous equations, inhomogeneous constant coefficient. We just use proposition 7.2.8 since from up here, each c sub k sub l is giving me a different element of my fundamental set of solutions. So I can extract a fundamental set of solutions from the theorem, this theorem right up here, 7.4.5. And then when I have a fundamental set, I just apply proposition 7.2.8 to solve the inhomogeneous problem. This is variation of parameters, is this proposition. Okay, so let's look at a nice example of this. And we'll do this completely by hand from the very beginning, but we'll see in higher orders we're going to want to use a computer to help us out. But from the very beginning, it's not hard to do these by hand, actually, for any second order problem. So I'll say any second order constant coefficients, ODE in one dimension is solvable by hand. And this is since the characteristic polynomial will be a second degree polynomial, and therefore we have the quadratic formula to give us our solutions. So let's go ahead and do this. If I start with my ODE, I convert myself to the characteristic equation, and all I'm doing is replacing, instead of y to the n, I'm replacing that with lambda to the n. And that gives me lambda squared plus 2 lambda plus 1. There's a lambda to the 0 power sitting around, equals 0. And this can be factored really easily to lambda plus 1 squared equals 0. And therefore, I have a lambda equals -1 is a root, and it's a root of multiplicity 2. Hence, my solutions must take the form, if lambda, right, lambda -1 with multiplicity 2, my solutions is c1 e to the negative t plus c2. I step up in powers of t. T e to the negative t. I have a habit of wanting to write lambda there. That's my general solution. So I'm going to scroll down now, and we'll see that that's we actually recovered there as well, right? So that's my general solution following the theorem. All I have to do is factor the characteristic polynomial and make sure I consider multiplicities correctly. Okay, so starting there and then extracting a fundamental set is a little tricky, but all we have to do is look at C1 and C2 and recognize that those are arbitrary constants. And so if I make this choice of letting one be 1 and the other be 0, and then swapping that procedure, I get two necessarily linearly independent solutions. Okay, so this is how we always find our linearly independent solutions. Alternatively, you can think about this like as a partial derivative in the Cj variable. If you took a partial derivative in C1, you would just recover e to the minus t. Partial derivative in C2, you would recover t e to the minus t. So either perspective is equivalently going to find you your fundamental set, which we get here to be e to the minus t and t e to the minus t. Extracted right from here. We're basically just looking at the terms with only each c being 1 and the rest being 0. Now we're going to make our lives a lot harder, right? So everybody, actually, I shouldn't say everybody can solve this, because I'm sure there are a lot of students in Math 340 right now struggling on this problem. This is the most like standard problem for Math 340. This is kind of their bread and butter, is constant coefficients, ODEs in second order. So, you know, all your friends in Math 340 will be able to solve this one for you, and probably not too many others. I mean, they will know others, but they'll be struggling at it, and this one is like their favorite. But let's get a little bit trickier from there, because we are not Math 340. We are Math 345. And we can work with some higher order problems. So working with a higher order problem, constructing the characteristic polynomial is no more difficult, but maybe solving it is, right? So characteristic polynomial, I'm still just taking this every y with a derivative on it, I'm replacing with lambda to that derivative. So this is lambda to the fifth minus 3 lambda to the fourth plus 4 lambda cubed minus 4 lambda squared plus 3 lambda minus 1 equals 0. And that is my characteristic equation. If I plug that into my computer, I'm going to get some roots of that equation. If I ask my computer to factor that for me, it's going to tell me it factors as lambda minus 1 cubed, lambda plus I, and lambda minus I. And this is why all of a sudden it's important we know some complex analysis, so we can be comfortable with roots being complex in this case. So then I want to be careful, because I do have a multiplicity 3 here, which means when I construct my solution, I have to consider multiplicity 3. This is lambda for lambda equals 1. Multiplicity 3 on lambda equals 1 says C1 e to the 1 times t plus C2, I step up in powers of t, e to the 1 times t, plus C3, I step up in powers of t, t squared over 2, e to the t. And that is my multiplicity 3 solution. And then I'm going to recover the solutions of multiplicity 1, which correspond to I and negative I. I guess I circled those backwards, but you get the idea. C4 e to the I t plus C5 e to the minus I t. So that's going to be my solution once I've factored my characteristic polynomial. Erase these now. And scroll down and see that that's actually what we recover here. There they are. I've swapped 3, 4, and 3, 5, or C4 and C5 around, which is just fine. But there's my solution, and in fact, once again, each of the C's is basically giving me an element of my fundamental set, right? So all I'm thinking when I ask myself the question, who's the fundamental set, I'm just going to grab the coefficients on each, whatever you would call the functions on each C, right? So that's all I'm looking at, is these are the functions which multiply each C, and that's going to give me a fundamental set of solutions. There's my 5 elements of my fundamental set. Okay, so that's actually all I have. It's a little bit quicker today. I hope you enjoyed it. I'll see you in class. Bye.